Good day, everyone. Thank you for joining us today. We are Group 11 and we will be presenting ICP-OES, Inductively Coupled Plasma Optical Emission Spectroscopy. Our presentation will cover its underlying principles, key instrument components, advantages and limitations, and its application in a large horticultural soil experiment for NPK analysis. We hope you find our discussion informative and engaging.
In preparation for a large horticulture experiment, a chemist was tasked with fully determining the NPK content of soil gathered from a large ice-filled area. Since nutrient levels will directly influence fertilizer planning, crop performance, and the reliability of the experiment's outcomes, the analytical results must be accurate and scientifically defensible. However, this task presents a major analytical challenge. Nitrogen, phosphorus, and potassium exist in soils in varying chemical forms and at concentrations ranging from trace to relatively high levels. Additionally, soil is a complex matrix containing metal ions, organic matter, and silicates, all of which can interfere with detection. Therefore, the instrumentation chosen must be capable of multi-element detection while maintaining strong selectivity and low detection limits. To systematically evaluate the available methods, our group established a prioritized set of analytical figures of merit. Accuracy was identified as the top priority to ensure correct fertilizer recommendations and experimental reproducibility. Sensitivity and detection limits are essential for detecting nitrogen, phosphorus, and potassium across agronomically relevant ranges. Selectivity ensures that the instrument can distinguish target nutrients from complex matrix components. Precision is needed to produce consistent results across the large number of soil samples required. Since the sampling area is extensive, high throughput and reasonable cost per sample are also important considerations. Finally, robustness and matrix tolerance are necessary for handling soil digests that contain heavy minerals and organic matter without compromising data quality. By grounding our evaluation in these figures of merit, we establish a clear and cohesive basis for determining which instrumentation is best suited for comprehensive NPK analysis in large-scale field conditions.
As said, the chosen instrument is ICP-OES, or Inductively Coupled Plasma Optical Emission Spectrometry. It is an analytical instrument that simultaneously measures the concentration of multiple elements in liquid samples by exciting atoms and ions in a high-temperature argon plasma and analyzing the characteristic wavelengths of emitted photons. Now, let's talk about the main parts of the ICP-OES instrument and how each component contributes to the analysis. We begin with the sample introduction system. Since ICP-OES works with liquid samples, the solution is first drawn into a nebulizer, which converts it into a fine aerosol mist. This mist enters the spray chamber, where only the smallest and the most uniform droplets are allowed to pass through. This helps ensure stable and consistent sample delivery into the plasma. Next, the aerosol enters the heart of the instrument, the plasma torch. The torch is made of concentric quartz tubes where argon gas flows. When the argon is energized by the radiofrequency generator, it forms a plasma that reaches extremely high temperatures. Inside this plasma, the sample droplets are completely vaporized, and the atoms become excited or ionized. As the excited atoms return to their lower energy states, they emit light at wavelengths unique to each element. That emitted light travels into the optical system, also called the spectrometer. Here, a diffraction grating separates the light into individual wavelengths, allowing the instrument to isolate the emission lines for elements like nitrogen, phosphorus, and potassium. The separated wavelengths are then measured by the detector, commonly a CCD detector. This detector converts the light intensities into electrical signals. Finally, the computerized control system processes these signals, compares them with calibration standards, and calculates the concentration of each element in the sample. To summarize the flow, the sample enters through the nebulizer and spray chamber, moves to the plasma torch where it is excited. The emitted light is then separated in the spectrometer, detected by the CCD, and then interpreted by the software. Together, these components allow ICP-OES to perform rapid, accurate, and simultaneous multi-element analysis.
Before selecting our final instrumentation, we also evaluated other traditional and modern techniques used for soil nutrient analysis. Methods such as Gödel digestion and Dumas combustion are widely used for nitrogen, but they have shortcomings. Gödel only measures organic nitrogen and ammonium unless modified, while Dumas requires specialized equipment and only provides total nitrogen without distinguishing forms. We also considered other instruments such as ICP-MS and WIS-NIR spectroscopy. But ICP-MS is more sensitive and expensive than needed for macronutrients, and WIS-NIR cannot directly quantify and can only predict nitrogen, phosphorus, and potassium via chemometric models. Because of these limitations, these instruments were not ideal as our primary method. These considerations led us to select ICP-OES, which allows direct, simultaneous, and accurate measurement of nitrogen, phosphorus, and potassium with strong selectivity, low detection limits, and excellent tolerance for complex matrices, making it well suited for this large horticulture experiment.
I'll now discuss the advantages of ICP-OES, particularly for soil nutrient analysis. First, ICP-OES provides multi-element detection. It can measure many nutrients like phosphorus and potassium in a single run, and modern systems can even handle nitrogen. This saves a lot of time compared to running separate tests for each element. Second, it offers high accuracy and precision. Because the samples are digested and fully dissolved, the instrument can quantify elements very reliably, which is why ICP-OES is widely accepted in soil laboratories. Third, it is robust against matrix effects. The high-energy plasma lets the instrument tolerate complex soil matrices, including clays and organic matter, without heavily affecting the signal. Next, ICP-OES supports high throughput. Once digestion is done, the instrument can run many samples per hour, making it ideal for labs that process large numbers of soil samples. Another advantage is lower costs per sample in high-throughput labs. Even though the instrument itself is expensive, analyzing multiple elements at once makes the per-sample cost lower when many samples are processed. And lastly, it has established methodologies and standards. Most agricultural labs already use ICP-OES for nutrients like P and K, so its procedures are standardized and widely trusted. Disadvantages. Of course, despite the strength of ICP-OES, there are some important limitations to consider. First, soil samples require acid digestion. This step is time-consuming, requires hazardous reagent, and is usually the most labor-intensive part of the workflow. Second, ICP-OES is expensive to buy and maintain. It also requires a steady supply of argon gas, torch and nebulizer maintenance, and regular calibration, which adds up to operational cost. Third, it is not field deployable. Unlike portable analyzers, ICP-OES must stay in a laboratory with stable power and gas supply, so it cannot be used for rapid on-site screening. Fourth, nitrogen detection with ICP-OES is limited. Nitrogen has weak emission signals and is prone to background interferences. This makes nitrogen less reliable compared to traditional Gödel type methods, unless the instrument uses specialized torches designed for nitrogen detection or is a modern instrument. And finally, running costs can still add up, such as calibration standards, digestion chemicals, and sample prep supplies. To summarize, ICP-OES is a powerful multi-element technique that provides the accuracy, sensitivity, and throughput needed for reliable NPK analysis in a large horticultural soil experiment. Understanding how it works, from plasma excitation to optical emission detection, and becoming familiar with its key components, you can better appreciate why it performs so well in agricultural nutrient analysis. Although it requires sample preparation and has significant operational costs, its robustness, precision, and well-established methodology make it a dependable tool for comprehensive soil nutrient profiling. Knowing both its strengths and limitations allows laboratories to make informed decisions about when ICP-OES is the most effective choice for agricultural analysis. Thank you for your time. This was Group 11 presenting ICP-OES.